basic properties of the silicon. And here is the crystal structure of the silicon. And in this unit cell, we figure out there are 8 silicon atoms in this unit cell. And then we use this to estimate the atomic density. So it's the number 8 divided by the volume of this unit cell, which is this lattice constant 8 cubed. So then we get this 5 times 10 to the power 22 centimeter per cube. So this is the atomic density. And here I just make a correction of the last lecture. So here should be the shell electron density. So because each silicon atom will have 4 shell electrons, so it should be 4 times of this atomic density. So you get this 2 times 10 to the power 23. So the bond density will be just half of this, because each silicon will have 4 bonds, but those 4 bonds are shared with neighbors, so effectively you only have 2. So then let's call this shell electron density here. So just make a correction here. So here we talk about that 1 out of 13 bonds may be broken at room temperature. So this will give you the free electron and the hole. So once you have 1 bond breaking, then you will have a pair of electron and hole. So this is how you get some conductivity in the silicon. But I would say this is still pretty low probability. So the effective way to increase the electron density is by doping. And for electrons, we need to dope the donors. And that are the group 5 elements, like the phosphorus here. So if you dope the silicon with those impurities, then you can tune the electron density by the donor's density. So here we assume that electron density N equals to the donor density, ND. And for the phosphorus, we are going to give additional electron to the silicon. So you have this free electron. Question?
This question is like a little off topic, but could carbon and germanium be used as substitutes for silicon?
So carbon and germanium. So carbon, there are many types of carbon. So of course, diamond is not like silicon. It's actually, as we discussed, diamond has the same crystal structure as silicon, but diamond is too insulating. Germanium actually is one type of semiconductor, similar as silicon. If you look at the history of the integrated circuits, the first transistor made out of germanium instead of silicon back in, I think, 1945, around 45 or 46. The first transistor is made of germanium instead of silicon. But later people find better way to purify the silicon, as we show in the video, where you have the silicon cylinder made out of the sand. So then the silicon becomes a mainstream. But today, actually, the very advanced technology node that Intel or TSMC used for their 7nm process node, then they actually intentionally introduced germanium into the silicon. So right now the silicon substrate is not pure silicon, so it's like a alloy of silicon and germanium. So this is to improve the mobility of the electron. But this is a too advanced topic, so I will not talk too much here. So let's assume it's a silicon substrate. So then, similarly for the acceptor, this is group 3, like boron, and then this will give you additional hole to the silicon. And then we'll assume the hole density P equals to the acceptor density, which is Na. So this concept of the doping, which is very important, because this will define the type of the semiconductor. If you have more electrons, or let's say you have donors, then it's N-type. If you have more holes or acceptors, it's P-type. But still, the material is charge neutral no matter which doping you have here, because you dope the charge neutral atoms into the silicon. So still the whole system is charge neutral. So this is the typical range of the doping in practice. So like 10 to power 15 to 5 times 10 to 18 per centimeter cube. So this is the typical doping density. This is much higher than the intrinsic free carrier. The intrinsic electron or hole density is 1.5 times 10 to the power 10. So this is orders of magnitude higher. So that's why this can be a tuning law to determine the conductivity of the silicon by doping instead of the intrinsic carrier generated by the thermal energy. Okay, so this is the lecture 3, and then we started the lecture 4 in the last class. So lecture 4 basically is from the